Hi guys, this video is on Kronecker's theorem. I consider it to be one of the most important theorem in polynomials. Let us see why. Let us first revisit our basic goal. Our basic goal is finding the zero of polynomials. And the question is, does zero of every polynomial exist? And if so, where? The Kronecker's theorem just answers to this question. It states that f be a field and fx be a non-constant polynomial in capital Fx. Then there exists an extension field E of f, an extension field E of f, and alpha belongs to E such that f alpha equals to 0. That means alpha is the zero of f. So yes, indeed, zero of every non-constant polynomial in Fx exists. And where? In what field? Either in f itself or in an extension field E of f. Example, let us see an example. X squared plus 1 is a non-constant polynomial in Rx, ring of real numbers. Then imaginary unit I in complex number is a zero of x squared plus 1. I squared plus 1 is 0. We have C is an extension field of R, and the zero of this polynomial x squared plus 1 exists in C. Now we prove this beautiful theorem. First we have, from our earlier theorems, the polynomial fx has a factorization in fx into polynomials that are irreducible over f. And let px be one such factor. That means the polynomial px is an irreducible factor of fx. Then again, from our earlier theorem we have, the ideal generated by the polynomial px is maximal in fx. And this gives us the factoring fx by the ideal generated by px is a field. We have a field here, and we claim that this field is the required field. This field is an extension field of f where a zero of fx exists. First we show the field fx by px is indeed an extension field of f. That is, f is contained in the field fx by px. For that, first let xi from f to fx is a function such that xi of a equals to the coset a plus px for all a in f. Then xi a plus b equals to xi a plus xi b, and xi a b equals to xi a xi b from the coset operations. And this shows xi is a homomorphism from f to fx. Third, we have xi a equals to xi b implies the coset a plus px equals to the coset b plus px. And this implies a minus b plus px equals to px. Here we have a and b are the constants in fx, and the only constant in the ideal px is 0. So we must have a minus b equals to 0, and this implies a equals to b, and this shows xi is one-to-one function from f to fx. And this shows f is isomorphic to this subfield of fx by px, the subfield of the cosets a plus px for all a in f. So f is recognized by this subfield in this field fx by px, and this shows f is indeed contained in this field fx by px. So the field fx by px is indeed an extension of field f. Second, we find a zero of f in the extension field fx by px. For that, suppose alpha equals to the coset x plus px. This coset belongs to the extension field fx by px. Suppose the polynomial px equals to a naught plus a1x plus an xn. Then phi alpha from f to fx by px is the evaluation homomorphism. Second, we have phi alpha of px equals to a naught plus a1 coset x plus px plus plus an x plus px to the power n. Now, in the factoring fx by px, we can compute this expression by choosing the representatives from the cosets. From this coset, x is the representative, x is a representative, and from this coset, xn is a representative. Now we have phi alpha of px, that is p alpha equals to a naught plus ax plus plus axn plus px. This expression is equivalent to this expression, and that equals to this much amounts to px plus the ideal px, and that equals to the ideal px, and that equals to 0 in factoring fx by px. And finally we have p alpha equals to 0 implies f alpha equals to 0 because P is a factor of f, and this shows alpha is a 0 of f, and we have found a 0 of f in the extension field of f, that is fx by px, and the Kronecker's theorem is proved.